Well, hello. I wanted to make this quick video so I could include it. All right, so power functions. We've moved on to something called power functions. So here we go. Let's talk about this. Which graph represents this function? So really quickly, and we'll go over this in more detail. Function notation. When you first see this, you might have thought it was f times x, but we read that f of x. F of x. It just means a function, and the variable is x. So that's what's going to change, and then something is being done to it. That's kind of the big idea behind function notation. So it's similar to y. It's the output. This is the output, and x is the input. So you put in something for x, there it is, and then the output is what happens when you're done cubing it and then multiplying it by -1/2. So one of the key things here is we're going to start to look at what is going on. What do the numbers do? What do when to our variable x? So what does a cube do to x? Well, it makes it behave like this. Bloop, bloop, right? Bloop, bloop. Think of a dance. Okay? The end behavior goes in opposite directions. What does that mean? It means, well, if one is going up, like if we're going to the right, or as x goes to positive infinity, it goes up. As we go to the left, as x goes to negative infinity, it goes down. Okay? So they go opposite directions. Now, that's the normal way. As x is getting positive, y is getting really positive. As x is getting really negative, y is getting really negative. I don't know if my camera is reversed or not, but that's the idea. And use Desmos. Explore visually. Visualization helps us understand. Okay, so plug these into Desmos. And if you need help with that, please reach out. Okay? Next, the coefficient. Coefficient, the number part in front of the variable. In our case, it's -1/2. Aha! We'll talk more in detail about what's going on with graphs, but that we called that a reflection. Oh, maybe from geometry, but negative, does it reflect it? I don't know. You tell me. So now if it was going up, suddenly now as x is getting negative, it's going to get y is actually more positive. You can think about it mathematically too. If x is negative, it's a cube. So you'll have a negative times a negative, which is a positive, times a negative, which goes back to a negative, which then also multiplied by that negative. So we're back to a positive. So as x gets very negative or goes to negative infinity, y is actually going up to positive infinity. And then now we flip it. And so then as x gets positive, well, this final negative symbol means y, the output values, the f of x, the function, is going to go down to negative infinity. So that's just some key things. The next thing you want to think about is if you're asking for a graph without using technology. Absolutely, we can just plug this into Desmos and then come find one. But I'm just going to try to tell you before. So I'm looking for a graph where, let me see. Okay, so let me draw it because the camera is backwards. Something like this. I did a lot of talking there, just kind of maybe like visualization of the story, but you can use this and actually visualize. So we're looking for a graph like this. It's going to cross at the origin. What does that mean? Well, when x is 0, this whole thing is 0, so it's going to cross at the origin. That's terrible. Something like that. Boop, there it is. Oh, positive, so it's going to be like this, but flipped back normal like this. Boop. And even function or an even exponent. So now when it's an even exponent, even degree, both of the ends are going to be going the same direction. So again, we look at the positive coefficient, or that we look at the coefficient. If it's positive, they're both going up. They're both happy, happy, happy smile. But if they're negative, they're both sad, a frown. They're going to, okay, frowny face. It's their negative mode. And that just, again, talks about the end behavior. Okay. Boop. Okay, question 2. Let's take a look. Which graph? Okay, so again, let's now use technology. -2x cubed. Ooh, terrible. Okay. I typed -2x shift 6 to get the caret, the number 3, and here we go. Was that even the right one? Yeah, cool. So here is what you're looking for. This something sort of graph that looks like this. It's again, whoosh, as x goes to negative infinity, so as x gets more and more negative as we move to the left, I know my camera's reversed, y actually becomes positive or is positive, right? So if we go this direction, it's going to go to positive. If we go this direction, it's going to go negative. Kind of follow it. And again, remember, up here is when the output, the y values are positive. Down here is when the y values, the output, the f of x is negative. To the left is when the x values are negative. To the right, to the right, to the right is when the x values are positive. Okay. So again, use technology, and they're nice. They're great. It's an odd exponent. The degree is odd, so we know the end behavior. See how this end is going opposite? This is an even graph. They're both going the same direction, meaning the exponent is even. The degree of the function is even. This is odd because they're going opposite directions, even going the same directions. And now we know there's a negative number in front because it's sad. Positive number. How do I know this is negative? Well, if as x is getting negative, y is getting positive, then there's got to be a final negative to make the y, the output values, the f of x positive. This is normal. If see how these are negatives and negatives, though they match, it's an even degree. Positive and positive, the x is positive, the y's are positive. It's a not even positive. This is a positive coefficient. Okay, moving on. But again, you guys could crush this with some technology. All right, so this part we're getting a little bit more complicated. Steeper, we're going to use some adjectives. Steeper, what does that mean? Well, it means it's going to grow faster. Think of a line when it gets to polynomials. I like to think of a line because that makes more sense to me. This is steeper than, say, a line like this, and then this one has a slope of 0, and then like, look, we're going downhill. Well, the camera. So anyway, think about if you're climbing, what does it mean to be steeper? It's growing faster, meaning the height is changing faster than the horizontal distance. So think about it like that. If you're climbing something, if the height is changing at like a nice rate with the horizontal distance, it's not that steep, right? As you're walking forward, you're slowly going up. However, if the height changes but the horizontal distance doesn't, it's like you're starting to climb. So the steepest graph would have to do with the largest coefficient, and you can think of it like a slope. The higher the number by the x, the steeper or the larger the slope. You could graph some of these. Let's make this a squared. Let's make it a positive. Okay, now let's do a 4x squared. We would think if it's steeper, would it be on the outside or on the inside? I'll let you guys think about that for a second. Ooh, on the inside. Does that kind of make sense? It's steeper, right? So this is, let's just do the regular. Let's do 1/2. 1/2 x squared. Ooh, look at that. Nice and slow. Okay, so think what it means to be steep in these kind of graphs. Okay, the blue one is the steepest, then the red, then the green. Use technology to explore. Question 4, what is the end behavior? Okay, so if it's got an odd exponent, they'll be going opposite directions. If it's got an even exponent, even degree, same directions, the end behavior, the way the graph looks, they'll both be going the same direction. If it's even and it's positive coefficient, whoop, it's smiling, it's happy. If it's an even and it's an odd coefficient, boop, negative coefficient, it's sad. It's sad. Negative, okay? Boop, boop. For these graphs, boop, think of them as dancing, and you can even, I'll show you in a second, make them dance. They are going to go in opposite directions if it's an odd degree, an odd exponent. The end behavior, they're not going to be both going the same way. They're going to be going opposite, like the Egyptian dance, right? Okay. Oh, all right. So now I want you to talk about it in different vocabulary. This can be confusing. So let's just follow along. This graph says as x approaches infinity. So that's positive infinity. That's to the right. To the right, to the right. Positive infinity. They're just going to say regular infinity. They're just going to say infinity. They won't say this because we don't say like, oh, I have positive 2 children. Does that make sense? I just say 2. And if I so if I have negative, I do say I have negative $2, or I would say I owe $2. Temperature, you do say it's negative 5 degrees, but you would just say it's 27 degrees. You wouldn't say positive. Okay, so this is where x is going to positive infinity. So then, okay, as we start here, let's see where the graphs start on your graph. Trey says, oh, look, it's going to negative infinity. This is where y is negative. These are all the negative numbers. So as x approaches negative infinity, so that's this way, so I'm going to start right here and go that way. It's going up, 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 up. F of x approaches positive infinity. We'll keep practicing with this one. The way they write it can be confusing. And really all you're doing is talking about the graph in fancy math language. That's it. You're just saying you're just describing the graph. So if like somebody wanted to draw it, you could tell them, okay, so start up at the top left, slope down, kind of do like a little bloop bend, like a little weird looking S that's been stretched. It's going to cross at -1. And then you're going to kind of, looks like a chair maybe, and then the feet are going to go down. You're going to say like, how steep is it? But it's basically using math language to describe this graph to somebody so they could draw it. Maybe that helps, maybe not. So you'll be like portraits, but with math. All right, 5 minutes left. Perfect, so I want this video in the Nearpod for you guys to have. So hopefully it processes in time. Otherwise, I'll post it in chat. So thanks for watching, and sorry I couldn't be there. What is the degree of the power function represented in the table? Okay, so there's a fun process for this one. To me, it's just an interesting observation that this happened, and it kind of I don't know. Calculus is a scary word in math, but I don't know. I just wonder who thought to do this. Who in the world is like, you know what? Here's x, and here's my g of x. Think x, think y, think input. So you put the number in. Something happens to the x. You get the output, the final output. Who would have thought, I'm going to subtract and see what happens. So let me just subtract -8 minus 1. Well, that should be -7. -1 minus 0. That should just be -1. We'll have 0 minus 1. And then that should be 1 minus 8 is -7. Okay, we're just subtracting. So some key things, it needs to be stepped evenly. So these are all going down by 1. This won't work if you have like random gaps, random distances. You can't measure the change accurately. And then all you do is subtract the bottom one from the top one, or vice versa. You're just trying to find the difference in each change. So now we'll have -7 minus -1. So that should be -6. You'll have -1 minus, that should be 0. And then now you'll have -1 minus 7, so that should be +6. Oh, I did something wrong. What did I do wrong? Oh, no, I didn't. Okay. So then you just keep subtracting them. Maybe I should have written this out, but okay, so look, now this is first degree. If this number was the same and the first time you subtracted them, it'd be a line. And that makes sense because that's how we measure change. This much change in x, this much change in y, this much change in x, this much change in y. So the difference between each step should be the slope, should be exactly the same. If it was a parabola or a second degree, all of these numbers would be the same. Ooh, why? How does that happen? I don't know. I haven't really, because the second time, I don't know. I really haven't given this good thinking. It's just really an interesting pattern. Okay, -6 minus 0 is -6. I don't know why I switched to positive. 0 minus 6 is -6. So notice this is the third subtraction, so that means this is a third degree polynomial. All of the numbers, say we had a longer table, all of the numbers after you did subtract, 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 in this column, the third column, they would all be -6. Oops, that's a negative. I want to do some more investigations. That's the how. I'm not sure the why. I know what it's telling you, but the why, I just haven't had a second to really think about. So hopefully you're curious. Why does this work? Who in the world would have thought, you know what, I'm just going to keep subtracting their differences? Why would that matter? Open-ended. You guys think about it. That's what you're doing. Again, all I did was do -8 minus -1, which becomes a positive, so then you get -7 and so forth. And I just repeated that process until I got the same number. Take your time. I mess up a lot with the signs when I do this because, so anyway, thanks for watching.